Hi, Nicole. Can you hear me, Nicole?
I can.
Okay. Did you not get here on last Thursday?
No, I was not able to. I had a doctor's appointment.
No, that's fine. That's perfectly fine. You'll at least give me an audience to talk to. Okay. So, how are you doing with this? We only got about 2 weeks to go.
Yeah, I'm doing pretty good. The one due this weekend, I thought I looked at it and I thought it was gonna be so hard, and then I watched your recording and I was able to finish it in like 15 minutes. So it was really
That
nice.
was the solubility.
Yes.
Okay, you did okay on that. I graded that yesterday.
I didn't look at the grade, but I hope I did okay. I felt okay.
Yeah, I'll have to go back. I don't have my grade book with me.
I can look, I think.
I could probably find it faster than you can. Or maybe.
I'm not really good at this stuff. I don't know why it's taking me so long how to figure out
a lot of this stuff is not intuitive, especially with these labs, Nicole. So it's really not your fault. Solubility product, you got a 93 on it. Got a 93.
Okay.
Just looking, I'll be perfectly honest with you. You got the Châtelet you're going to need to bring that up.
Yeah, there was one lab I was so confused on, and I don't know why. Yeah, it was that one that I just completely.
Nicole, I don't have you for lecture, do I?
No, you don't.
Okay, this is just lab. All right. Do you have to take Chem 2 again? I'm sorry. No. I'm sorry. That's not what I meant to say. Do you have to go beyond this? Is this your final?
I think this is my final chem.
And you've gotten the lecture done with, right?
I'm doing the lecture right now.
With who?
Through UF, which is where I go to school.
Oh, okay.
They just don't offer the lab online, and I had to come home for the summer.
No problem. How are you doing in that class?
I have an 80 right now because the first exam was super hard, but then I studied for a week straight for the second one, and I ended up doing really well in it, so I'm really proud of myself. But
you should, Nicole. It should ease up on you. My guess is that you're at the same place we are right now. You're doing entropy.
We just moved on to. No, maybe that is what we're doing, like how to calculate it in all these different scenarios.
That would be delta G's, delta S's.
Yes.
Hi, Jolene.
Morning.
Just a second, Nicole. Jolene, you know that this is just a rehashing of what I went over on Thursday, right?
Yeah, I just want to watch it again. I'm old and have a very small memory.
No problem at all. This stuff is very easy. I was just telling Nicole, Nicole's in entropy right now. This is the hard subject of what's left. The only things you have after this are electrochemistry, which is fairly straightforward, and nuclear chemistry, which is a breeze. Okay, so you've gotten over the hump for this. Okay.
Awesome.
Anything either one of you have to shout at me? You know, Nicole, I'm available for discussion of Chem 2 at the UF course as well.
Thank you for that.
Okay, if that having been said, let me go find well, I gotta stop share. Thank you. All right. Yeah, Greg stuff. This. Okay, now I got to figure out what I called it.
The lab is starts with a V.
Yeah, I know. I can't believe it's not here.
Voltaic cells.
Is it? Yeah. Where's it at?
I don't know where it's at. I'm just
I'm sorry.
just playing the name game.
I thought I had it up there and you were.
You're in Pinellas County too. Are you worried about this tropical storm?
Not at all.
You're not?
No.
My
actually
parents have no idea what's going on.
I have. It's the tropical storm. It's going to come off the coast. We are on the bad side of it, but it's going to be a category 1 at the most. So no, I'm not worried about it.
I think my parents are just worried about flooding because we live on the water.
Yeah. I live 2 blocks from the water. It would have to get real high.
Right now I'm staying at my dad's beach house in Indian Rocks in the Narrows. So there's water in front of you and water behind you. And I'm like, oh my God, I think I should go home. But where I live in Tampa, I live in a flood A zone as well.
Oh.
So I'm in a flood A zone and I'm like, ooh. Usually nothing ever happens, but I'm worried.
It's going to be fine.
Narrows of Pinellas County.
Yeah, they're saying where I live, we're going to get like 4 feet of water.
Well, when they say 4 feet, you have to remember that the beaches are lower than the actual land. So
when it's supposed to hit where I live is already high tide at that time. So that's why they're a little worried. I live in St. Pete, like on the south side.
Oh, yeah. So you're in trouble.
Thank you, buddy. See you later.
Yeah.
Oh, so you live down in the Pink Streets?
Yeah, I live over by like Bonito Bayou. You know what it is?
I can't believe
That's
this.
Always smiling. I figured it out. I'd be smiling if I lived over there.
I'm sorry, guys. I cannot figure out where that PowerPoint went.
I have a solution.
What's that?
We just get A's.
Ooh, I love that idea.
My favorite letter, A plus.
You're getting A's anyway, Jolene.
I know, but I don't like a low A. I like a high A. I have an impression.
I can't believe I didn't save it. Okay, let's go in and figure out what we're doing here. Okay.
All I see on my end is grades.
Yeah, yes.
I think you should tidy up my grades while you're in there.
Sorry, I didn't realize I had that still in there.
Let's do some cleaning up while we're in there.
Where is?
Yeah, that's 66 out of 100. It's not looking really good right now.
Okay.
I totally agree with you.
All right, let's get out of here.
We should get an A for absolute participation.
All right, now the Redox Lab, the one I talked about on Thursday, that is a pain in the ass. It's got 8 pages to go with it, all right?
Oh, gosh.
So, yeah, it is a fair warning. That's part of the reason why I gave you extra time on it. Just to look at that. Okay, I'm pulling up the Redox Lab right now. It's really easy. You've had it before. It's single replacement reactions. Do you need help with that, Jolene?
I just don't like 8 pages because I hate to second guess myself. I'm insecure with my answer.
Report sheet. Thank you. Here is the report sheet. Actually, I was really encouraging you guys to not deal with to not do it because of the fact that it's a pain to grade.
I know
what he's done.
So when you see that we tried, just give us an A.
Yeah. Well, I did. Yeah. Jolene, What did you get on the last lab? The first
A
and
90
the second page.
a 92?
You got the full. If you put something into a box, you got the full credit for that.
Yeah.
How am I going to grade what you put down for a concentration? So as
You
long as you
can't.
filled out the box, you literally got 70 points of it. The only thing I was really grading were the questions afterwards. In any case, what you have to do, you have five metals, and you have 5 solutions. You have to mix the metal with each one of the other salt solutions. So for example, you have silver nitrate. You're going to mix every one of the other 4 metals with the silver nitrate. You have to do that in the simulator. And basically you have to give your observations. If it had a reaction, you got to put the net ionic equation. So you're putting copper metal in with silver nitrate. If copper is more active than silver, you will get a reaction. So the net ionic equation, right now you have Cu and you have Ag plus, because the silver nitrate is an ionic compound. So the silver exists as Ag plus. So your net ionic.
Would it go to copper? Would it go to copper 2 plus 2 copper 2 minus plus silver 2
plus.
silver nitrate plus?
Yes.
2 plus.
It would be copper 2 plus.
For nitrate negative.
No, it would be copper 2 plus, copper going to copper 2 plus, and the Ag plus going to silver metal, silver neutral.
Got it.
Okay. Zinc and silver nitrate. Zinc is a metal. It reacts to make zinc plus 2. The silver goes from Ag plus to Ag neutral. Are you seeing how that works, Jolene?
Yeah.
That's if you get a reaction.
If you get a reaction. And then if you get a reaction for the next one, it'll go Pb plus 2 plus. Or would it be Pb 4 plus?
You don't know that, but just put 2 plus.
Okay.
That's one of the reasons why this is unfair. You have no way of knowing whether it's going to lead 2 plus or 4 plus. Either answer would be accepted.
Okay.
Okay. So you have lead 2 plus plus Ag.
0. Yeah.
Okay. So that's the first part of this thing. You got all of these to go through. Then you have another set. And these you should pretty much be able to know right off the bat. Chlorine, bromine, and iodine. Which one is more electronegative? Chlorine, bromine, or iodine?
Chlorine.
Exactly. So if it's more electronegative, it's going to want to have the negative charge.
Yes.
So if I have, and between bromine and iodine, which one is going to be more active?
Bromine.
Bromine. It goes chlorine, then bromine, then iodine.
Yes.
So if you mix something, a bromine that is a negative with iodine, then what happens is the bromine is already negative. Since the bromine's already negative, nothing happens. Does that make sense?
Sure.
You say sure. Okay. Let me see if I can. Okay.
I agree with that because the bromine's attached to the sodium, and the sodium and the bromine are stable.
Well, it's not a question of the stable. NAI is a stable compound too, Jolene. But when you put them next,
strong enough to break up the bromine, so the sodium bromine.
Now, let me give you an example here, okay? You have a kid that's got his lunch money, right? All right, his guy has got his lunch money. He's standing in line. Bully comes over, a bully who's smaller than him. Okay, is the smaller bully going to be able to take his lunch money?
No.
So in this case, the smaller bully would be iodine. The kid with the lunch money would be the bromine because he's got the electrons. Okay. Mm-hmm. Now you come across that same kid with his lunch money. A bigger bully comes over and still tries to get his lunch money. Is he going to be able to grab that lunch money from him?
He'll be able to grab $1.
$1?
1 electron.
Okay. Thank you. Thank you. Good continuation of the analogy. So in that case, that would be like bromine. Bromine would be like the kid with the lunch money. The bigger bully would be chlorine.
Yeah.
So chlorine's able to grab the lunch money from bromine. However, iodine is a smaller bully, so iodine is not able to grab the lunch money. Does that seem to make sense?
Yep.
So basically we have bromine with iodine water and chlorine with iodine water. Neither one of these are going to give a reaction. You have iodine with bromine.
Reaction.
Now you have a kid that's being attacked by a bigger bully. The bigger bully is going to be able to steal the electrons from iodine and keep them for himself.
Mm-hmm.
Jolene, are you trying to keep your face from being seen, or are you?
No, I'm holding my phone just big.
Okay, does that kind of make sense to you?
Yeah, makes great sense. So we're going to see a reaction now. Are we doing this inside of something or just doing this out of our head?
You're doing this in the simulation.
True.
Okay, then you're going to have all of your ions for the metals, and you have to rate them. Just put the metals down here, and all I want you to do is just say, just list them down in here, the most active to the least active.
Got it.
What the SOA means, strength of oxidation, a strong oxidizing agent, weak reduction agent. Okay, don't pay attention to this. What I want you to do is just put the most active to the least active. Fair enough?
Mm-hmm.
You're going to do the same thing for this one. For this one has to do, you can answer this already. You've already answered it. Chlorine is more active than bromine, which is more active than iodine.
Perfect.
Okay. Now, you got to be careful about this. What you're doing, you're saying, K, can it be an oxidizing agent? Now, the person that developed this terminology should be slapped, shot, and buried because it confuses the snot out of everybody. If something is an oxidizing agent, it causes something else to be oxidized. So in fact, it is reduced. Are you understanding what I'm trying to say here?
Yes. And the answer is yes.
Remember,
potassium.
An oxidizing agent means it gets reduced.
So it gains an electron.
Yes.
But it can get.
Jolene, can potassium ever gain an electron under normal circumstances? Good. You cut out.
Is potassium in the second row?
Yeah, but it's all the way over on the left side.
Okay, it's stable.
So is potassium ever going to grab an electron?
No.
It will never grab an electron, so it can't gain electrons. Okay, Jolene?
Mm-hmm.
So it can't gain electrons. That means it can't be. So you're going to say no. When you say no for potassium, you don't have to fill out the box right beside it. Now, can potassium act as a reducing agent? Can potassium lose electrons?
Sure. Potassium chloride.
So the oxidation half reaction would be K yielding K plus an electron. Okay.
Next one, tricky.
I'm sorry, the next one?
Iron 2 plus. Is there another state in iron? Is there an iron 4 plus?
Iron, no,
so it can,
three plus.
3 plus. So it can be an oxidizing and a reducing.
Exactly. Exactly. The Fe2 plus can be an oxidizing agent. So it would go from Fe2 plus 2 electrons yielding iron metal. But it can also be a reducing agent because it can lose another electron to go from Fe2 plus yielding Fe3 plus an electron.
Oh. And that's what you mentioned last time as rust?
Yes.
Okay.
Okay. A lot of these are manganese, can go both ways. No, I'm sorry. In this form, it can't. It can't go higher than a +7. But these are things that you guys don't know. Manganese cannot go higher than a +7. If you look at the, do you have a periodic table with you?
Have to Google.
If you look at where manganese is in its outer row, it can have 2 4s electrons and 5 3d electrons for a total of 7 electrons in its outermost shell. So it can at most lose 7, or in other words, be a +7. Does that make sense?
Mm-hmm.
It cannot lose any more electrons. So if it can't lose any more electrons, it cannot be oxidized further, so it cannot act as a reducing agent. However, it can act like it can act as an oxidizing agent because it can go from Mn +7 to Mn +2. Are we good on this?
Yeah.
And he gives you this last question. All right. A is green, B is yellow, C is red. If they exist as the ion, they're colorless. Okay? Those are the rules we have set here. Okay? If a solution of C is mixed with one with B minus, the color changes from red to yellow. What species gives a yellow color?
B.
B gives a yellow color. So the original problem said C was mixed with B minus and the color went from red to yellow. So did I produce B?
You did.
Did I have a reaction?
You did.
So which species is oxidized? Which one?
Red.
Which one gained electrons?
B.
B didn't gain electrons. B
is neutral form, so B lost it.
B lost electrons.
The B was oxidized and C was reduced.
B was oxidized. C gained electrons. It was reduced.
Yeah.
When you mix C with A minus, it stayed red. Did I have a reaction?
No.
No.
C with A minus, no.
So Is C a better oxidizing agent than A? In other words, if C is placed in presence of A, will C
No.
get reduced? And the answer to that is no. Is C a better oxidizing agent than B? Will C in the presence of B minus become reduced?
Yes.
Yes. So you have to arrange A, B, and C in order of increasing strength as an oxidizing agent. 8 pages. I'm sorry. You got to go through and I got to see how I'm going to get out of here now. Okay, stop share. Okay. Yeah, I don't know how. Yeah, this is what I got. Yeah. Okay. I didn't want to get out of my HCC. I had to think about doing that.
He had never been a part of Spears' 13-year conservatorship nor its operations, adding, as her manager, I believe it is in Britney's best interest for me to resign from her team, as my professional services are no longer needed.
Nicole?
Yes.
Nicole, is that TV on in your house?
It is.
Is there any way to turn it lower? I'm sorry to
I
ask.
can. I didn't realize you could hear it. I'm sorry.
Thank you.
You're welcome.
Okay, so I'm getting in here. All right, so that's everything that's involved with that lab except the simulation. And yes, I realize this is going to be a pain, but it's something you're going to have to deal with. And Chem Collective.
Can't we go through the lab and the ones that we know that there's no reactions, just put no reaction and skip over that?
How am I going to see that, Jolene?
Huh?
Jolene,
Yeah?
how am I going to see that? How am I going to see that you haven't done the lab?
Yeah, exactly. But I'll go through and do the ones that have color changes in case they have color changes. That will save us time, Nicole.
I like that idea.
Oh, this is the walkthrough now. I don't need this.
Such a bad influence, ruining the young generation.
I don't mind.
It's not cheating if you already know.
Good point.
Why is... Okay.
I hate labs.
Yeah.
Wish we were in the real lab.
So basically, you're going to take silver chloride and you're going to get to the stock room. And am I in the right lab?
Nope. You're in last week's lab.
Thank you.
You're welcome. That looks mighty familiar because I kept going through and making sure because I wasn't sure when things were stable. And I was like, man, are these numbers right? Because I realized that some numbers were the same and some were different. So I had to Google and see if some numbers were supposed to be different. And it said yes. And so then I went back through because I was trying to keep adding solution until they became the same numbers like the first two.
No.
I didn't know. But guess
I
what?
told you. I specifically told you to dump
I have a short-term memory.
I told you to dump 1/10 of a gram in there and then add a little more, and you would see that the concentrations do not.
I waited till they stalled at 4 significant figures, and I called it a day at that point because they would flicker. I don't know why they flicker. They should just stabilize. It's a computer, for Christ's sake.
All right. Solids. Silver metal.
All right.
Okay. Stock room. I don't need solids. I need liquid solutions.
Hey, where did you turn the lights on? Lights on.
Okay. Copper nitrate. Okay. So basically you're taking the copper, notice the blue color, you're taking this and you're adding some to it.
I'll turn mine down. I'll turn mine down.
Okay, and pour. Okay. Pour.
Que hora é agora?
8:41.
Tá bom.
Why is this not doing anything? Okay, we've added 2 grams. Okay. Okay. I'm getting no reaction here. Do you see that?
Mm-hmm.
I keep on dumping stuff in and I'm not getting any reaction. Okay, so that's copper, silver with copper nitrate. There's a reason for that. Okay. Now I'm going to add my 1 gram. I'm not getting any reaction here. Okay. It's staying the same. Both times I added silver to that, it stayed the same. Now we are going to add a metal. Another metal. We are going to add copper, and we're going to add this to
Bromine.
silver nitrate.
All right.
Okay. I'm adding copper to silver nitrate. 1 gram pour. Ooh, look at that.
Voila.
Got a blue color. Okay. Had a reaction. Basically, the copper has gone into solution to make the blue color. Any questions about this?
Mm-mm.
Pay attention. Pay attention to the temperatures. Okay? Pay attention to the temperatures. If the temperatures go up, consider that to be a reaction.
Okay.
Anything else with the Redox Lab?
No, I think I got it.
Nicole?
I think I'm good.
Okay, so I'm going to get out of this one. Stop share first. And I'm going to get out of this lab. And we're going to go to the next one. Okay. All right. Now, what happens when we are dealing with electrochemistry? What we're about to talk about explains why one thing is more active than another. Okay? If you notice, all the reactions that are in this table, are reductions. I have things that are gaining electrons to become neutral stuff. Okay? Now, every one of these reactions are compared to this one. 2 H pluses plus 2 electrons making H2. They've set that at 0.00. That means every other time that you have another reaction, we compare it to the standard hydrogen electrode, or SHE. So if I put lithium in one cell and hydrogen in the other, there is a voltage difference of a negative 3.04 for the lithium. Now, in order, you're going to go over this probably on Thursday or next week. In order to have a spontaneous reaction, and we're all about spontaneous reactions here. In order to have a spontaneous reaction, the potentials have to be positive. Have to be positive. Now, if I switch the reaction from lithium ion gaining electron to become lithium metal, if I switch that around to lithium metal yielding lithium ion plus an electron, I switch this potential from negative to positive. Okay? Is that making sense to you?
Yes.
What we want is we want positive voltages. And the other rule is we have to have an oxidation reaction and we have to have a reduction reaction. I can't have two reduction. I can't have two oxidations. So one of these reactions has to be shifted in order to get a positive result. Now, if I am linking aluminum with copper, aluminum as a reduction reaction has a negative 1.66 volts. Copper has a positive 3.34 volts. So in order to get a positive number, am I going to shift copper or am I going to shift aluminum?
You're going to already have a positive number.
Jolene, I need to add them both together.
You have a positive 3 point something, a negative 1.7 or whatever you said. That's already a positive number.
Nope. I'm sorry, you're not seeing the screen?
No, I'm seeing your face.
Okay. Let's get back to that. Okay. Do you see the table that's in front of you? Okay. Now, the rule is I have to shift one of these reactions. Right now, they are all of these reactions are reductions. They're all gaining electrons. I can't have a reduction without an oxidation reaction.
So you're going to shift the smaller number.
I have to shift the more negative number.
That would be smaller.
Okay. I wanted you to understand that it was more negative. You are correct. I wanted to make sure that you were understanding it correctly.
Yeah.
So if I have aluminum that has a negative 1.66 volts, and I have a copper that has a positive 0.3 volts,
We're going to shift
which one do I have to shift?
The negative 1.66.
So what that means is I have aluminum going to aluminum plus 3 electrons.
Which will
I
give
get
you
a positive 1.66. I link that with my copper reaction, which is a positive 0.34. The overall potential of that cell is going to be
2.
2. Have you got that, Nicole?
Yes.
Okay. Now,
Give her.
so if you have chromium and nickel, Nicole, you have chromium, which is a negative 0.74, and you have nickel, which is a negative 0.26. Which one of them are you going to have to shift so that you end up with a positive result?
The chromium?
You're gonna flip the chromium. And that means you're going to have Cr yielding Cr plus 3 electrons. But now you have a positive 0.74 voltage, which means when you link that with the nickel, you have a positive 0.74 plus a negative 0.26. You overall have a positive 0.48 as your standard cell potential. Is that making sense to you?
And
Yes.
just to get it straight, the positive is the cathode and the negative is the anode?
No, it depends upon whether your reaction is being reduced or oxidized. The easy way to remember that: anode, oxidized. Both of them begin with vowels. So
right.
At the anode, you have the oxidation reaction occurring.
And for us, it was the one we reversed.
In that case, we're going from copper, to copper plus 3 electrons. That is being oxidized. The chromium is the anode.
And the anode and the cathode, that is good for what? Like electro?
That shows you the direction of the circuit.
Yeah, electrostatic.
Electrons always go from the anode to the cathode.
Anode to cathode, okay.
And what it does when you get actually into describing the electrochemical cell, what's happening at the cathode is you are having a reduction.
Is that for like DC current only?
Not a clue. I think these are all DC currents.
Has to be, because alternating current, you can go back and forth, right? I'm sorry, I'm getting really too far on this. Just keep going.
Jolene, we don't
Curiosity always kills this cat. I could really go off on a tangent and I need to not. Just keep going.
What you're dealing with right now is you're dealing with physics.
I understand.
The physics aspect of electrochemistry.
Yeah.
We don't have to deal with that. Okay. So we're not going to deal with direct current, alternating current. We're dealing with direct current.
It has to be direct current here.
And batteries are all direct current.
If not, it would kill you. Yeah.
Pretty much. That's why Tesla's was better than Edison's.
Absolutely right. That's why we use all his patents. You know, he died penniless. Poor Tesla.
Poor Tesla. What can I tell you? Go down to the Edison Museum. They talk about that there.
I need to do that.
It's actually a fascinating place to get to.
Isn't it the museum?
I'm sorry?
Isn't it the Edison Ford Museum? Don't they have stuff there? Yeah, I heard about it. I had just never been.
It really is it's a good 15-minute trip off the highway to go see for a half an hour. The grounds are gorgeous.
That's what I heard.
Okay, so what happens? Just realize what is happening here. When you have a reduction, the copper plus 2 electrons is getting to be what you're making is copper metal. So what's happening at the cathode is the reduction reaction. You're producing copper metal. It's plating out on the electrode. All right. Does that make sense, Jolene?
Yeah. So now let's make another question. Like, you know, those things they put on you when they like shock your heart?
Yeah.
That would be the cathode would be on your chest and the anode would be on the machine.
I think that both of them are on your chest.
The cathode and
yes,
both?
Because what they do is they push.
But they want
it's not a battery. At that point, Jolene, it's not a battery. They're literally pushing an electron circuit to go from one thing to the other, and it goes,
other, right?
It goes through your heart at the same time. Your body is filled with electrolytes, so that conducts the current.
Gotcha. That makes sense. Sorry, this is fascinating.
No problem. Now, if we look at the other reaction, chromine metal is now going to chromine ion. So what's happening at the oxidation or the anode is the chromium electrode is being eaten up and the chromium metal is going into solution. Does that make sense?
Mm-hmm.
And that's just basically a electrochemical cell. But let's look at what else is happening. And I'm going to stop share and I am going to grab any old PowerPoint so I can talk about things. Okay, new slide. Okay, so we had Cr3 plus 3 electrons going to Cr. And this was a negative 0.76 volts. And I think it was nickel. Wasn't it nickel we had?
Mm-hmm.
I had nickel 2 plus 2 electrons.
We need screen share.
Ah, thank you. Okay. Okay, this is what originally we had. Wasn't it this and this?
Yeah, let's say so.
All right, this is what we originally had. And so we said that we can't have two reduction reactions, so one has to be an oxidation. So I have to literally change this one around to be this. Okay, do we understand? We had to change the top one to the bottom one.
Would the CR become negative on the bottom one?
What's that?
Would the CR become negative on the bottom one?
Nope, because the CR is losing electrons. It's being oxidized. The nickel is being reduced.
I understand. But the top one, you have Cr3 plus 3 electrons equals a positive or neutral Cr. When you're doing the reverse, shouldn't it be balanced out in the reverse to get that positive charge?
There's no positive charge here. Do you see the positives from the ion get balanced by the electrons? Okay, Jolene? I have 3 plus.
I'm not buying it, but if you say so, I'm not convinced.
I have 3 pluses plus 3 negatives. 3 pluses and 3 negatives are neutral, right?
That's sure.
So that's why the top one is balanced.
But it spits out a negative voltage. And then you're saying if you reverse the voltage.
If you reverse the reaction.
Exactly. Then you would reverse the voltage.
Correct.
Okay.
All right. Now, let's look. I'm going to take this away for a second. If I add these two reactions up, if I add the two reactions up, don't I get Ni 2 plus Cr yielding Ni plus Cr 3 plus.
And you're missing an electron.
We'll get to that in a second.
Equals
Okay.
50.
I'm sorry?
Equals 50 voltage.
Equals
48.
right?
Okay, and then what about the electrons? Do you balance those out?
Ah, very good. Smart girl.
Sometimes.
You cannot have electrons being created or being destroyed. So what we have to do is we have to balance the electrons. I have 2 electrons in the top reaction. How many do I have in the bottom?
3.
So I have to multiply this whole thing by 3.
And
I
the
have to
bottom one.
multiply this one by 2.
Yeah.
Are you still seeing the screen?
Yeah.
Okay. So if I do that, this means I have 3 of those, 2 of those, 6 electrons, 3 of those, 2 of those, and 6 electrons. Okay.
Yeah, I agree.
All right. Now, this is foreshadowing oxidation reduction chemical equation balancing, because this is exactly what we're going to do when we balance equations. If you look, this entire equation now is balanced.
Yeah.
Now let's look at what the equation is telling us. This is the way the reaction goes spontaneously. So I've got chromium metal reacting with a solution of nickel ion. Did the reaction go?
Yeah, it went.
It went because I got a positive voltage here, right?
Yeah.
It
Wait, what does
went-
E to the 0 mean again?
That's the standard potential, the standard reduction potential for this cell, standard cell voltage.
Got it.
Okay. You're going to need that in a second or two.
Okay.
So it's positive going in this direction. Will the reaction go in the reverse? If I take nickel metal and put
It
that
will
in
not.
solution. Nicole, do you agree with that?
Yes.
All
I
right,
think
so it goes in this direction. Now, let's see what that means. I'm putting chromium metal into a solution with nickel ion. I got a reaction. Which one is more active, chromium or nickel?
Chromium.
Nicole, do you buy that?
Yes.
I don't know. I don't know. We had to reduce the nickel. That's the cathode.
Remember,
the cathode has the electrons that go to the anode.
anode.
Wait, explain that part.
No. Anode has to react. Look, what's
Oh, yeah,
producing?
AO,
What is
AO
producing the
has
electrons,
electron.
Jolene?
So the chromium is more reactive.
No. The chromium. I'm sorry. Yes, you are correct.
Because that's the one that has the electrons going to the cathode. Can we look at it that way?
If you want to,
May not be.
I would rather you look at it like the reaction is positive going in this direction.
Exactly.
Okay. So what is happening is my chromium is being oxidized. My nickel is being reduced. My chromium is ending up ionic. Because my chromium is ending up ionic, it is more active. Did you see my logic there?
I did.
Basically, this explains why activity series are the way they are. You can now look at I'm going to stop share for a second. You can now look at this table. You can now look at this table and you can draw the activity series. If you put lithium with aluminum, don't you have to flip the lithium?
Yeah.
And then the lithium metal is making lithium ion.
And then you'll end up with 3 lithium plus 3 electrons plus 2 aluminums plus 6.
No, just
electron.
one aluminum. One aluminum.
Oh, I'm sorry. I don't know why I see a 2. I saw your arrow. I'm blind. Yeah, you're right. Just one of the rest, and then you'll get the reaction of that, whatever that bounce.
If we go, as we go up this chart, okay, as we go up this chart, as we're making a more negative reduction potential, those particular metals are going to be more active. If I compare—
Okay, here's a question for you. Let's go down to the bottom and go 2 up, where you have the 0 charge and the +3, 4. You cannot make that work and have a reaction because one cannot be reduced.
Wait, what are we talking about?
Go all the way down to the bottom, go to the copper and the 2 hydrogen. You cannot do anything to those 2 to make,
Oh, yes, you can. One of them has to be flipped.
Well, if you flip it, you can't put a -0. 0 is just a 0.
Yeah. But you're still flipping it.
I've never heard of a -0.
No, it doesn't mean it. Yeah,
you still flip the reaction, so then you have the H2 goes to the 2H.
Jolene, mathematically, if you multiply -1 times 0.00, you still get 0.00. The standard reduction of that cell would be a positive 0.34.
Okay.
No matter whether this reaction is in this direction or if this reaction is flipped, you still have a reduction potential of 0.00. It's just going to be the one that is oxidized as opposed to reduced.
Okay.
Nicole, you still with me?
Yes, sir.
Okay. So we're all good about this. Just to give a summary, if I'm given a standard table like this, I'm going to look at the reduction potentials. I'm going to see the reduction potential that is the more negative, and I'm going to flip that reduction reaction to be an oxidation because I have to flip one of them. Therefore, I have now identified my oxidation reaction and my reduction reaction. I add the voltages after flipping, and that is going to be my standard reduction potential, my standard voltage of my cell. By standard voltage of the cell, that means I have 1 molarity of the ion solution.
All right.
Where the oxidation is occurring, that is the anode. Where the reduction is occurring, that is the cathode. The easy way to remember that is vowel to vowel, consonant to consonant.
Yeah.
You can look and see which metal is more active by looking at the table. The further you go, the further you make a number negative, that is the more active element or metal. That's all we've done to this point. Okay? Are you on a solid basis now?
Mm-hmm.
You understand what's going on?
Mm-hmm.
Nicole, Jolene?
Yes.
Mm-hmm.
All right. That is for a standard cell. All I've been talking about so far are standard cells. This means when I put my lithium metal, my lithium electrode in my lithium ionic solution, my ionic solution for that lithium is 1 molar. When I put my copper metal electrode into its solution. The copper ion solution will be 1 molar. I do that, and I end up with my standard cell potential, which is going to be positive 3.04 plus a 0.34 or a positive 3.38. We're all understanding where I'm at right now, correct? All right. Now, we have to understand what's happening under non-standard conditions as well. Under non-standard conditions, my E cell is going to be equal to my E0 cell, the standard cell, which we just figured out. So that's what the E0 cell is. That's our standard, my cell under standard conditions. To that, I'm going to subtract RTNF times the ln of Q. All right. If I do that under conditions that are 25 degrees Celsius, I can change this RTF term to negative 0.0592. So then, in order to figure out what my cell under non-standard conditions are, I'm going to have to take my standard cell potential, and I'm going to need to subtract out my 0.0592.
They use 0.01.
I'm sorry?
Okay, 0.0952 is all that jumbo?
Yes, that's because they're not doing it under the standard temperature. Okay. And I'm just checking something because I want to make sure I'm not giving you bad information on the plus or negative. 854, okay. Okay. If you're running the reaction at 25 degrees Celsius, okay? This is not 25 degrees Celsius. 295, 25 degrees Celsius is 298 K. Okay, Jolene and Nicole?
Mm-hmm.
If you are running it at room temperature, 25 degrees Celsius, which is where most of these reactions get run, you can reduce, at that point, the R, the T, and the F. R, T, and F become constants. T is 298 K, R is going to be 8.321, and F is a constant of 96,500 coulombs per mole. Okay?
And 2 moles because each reaction has 1 mole each?
Forget the 2 moles. Forget the 2 moles for right now. That is not going to be a constant. Okay? Are you with me, Nicole and Jolene?
Mm-hmm. I think so.
I'm trying to make things easier for you. What we are going to do is we're going to say we're doing this under temperature of 25, room temperature. If we do it at room temperature, then the 8.321 times 298, which is 25 in Kelvin, divided by 96,500, that equals a number 0.0592. Write that down, 0.0592. So I basically simplified this equation. That equation that I'm highlighting, I've simplified that equation to be E cell is equal to E0 cell, the standard potential, minus 0.0592 divided by N times the ln of Q. We're going to stop share here for a second. And I am going to make a new slide. Nernst equation. E cell is equal to E0 cell minus RT divided by NF times the ln of Q. All right?
Can't see it.
You can't see it. Thank you. Thank you.
You're welcome.
Okay, so this equation is what is in your handout.
Mm-hmm.
What I'm saying is that if I'm at 25 Celsius and I change ln to log, I simplified this top reaction to E cell is equal to E0 cell minus 0.0592 divided by N times the log of Q. This is the original equation. I am saying I'm at 25 degrees Celsius, which is room temperature, which is where you conduct most of your reactions. And the other thing I do is I'm going to change ln to log. There is a mathematical conversion you can do that. And I also incorporate R, which is a constant, and F, which is a constant. I can simplify the top equation to the equation you see right before you, okay? Now, N is the number of electrons exchanged. Q is the equilibrium expression. Okay? Are we good with that, Nicole and Jolene?
Yes.
So the only thing I have to do at this point is I have to figure out the number of N, and I have to figure out what Q is. And it can be a little bit tricky, but we're going to get through it. Because remember, these are my overall reactions. I've got 3 Ni2 plus 2 CRs plus 6 electrons yielding 3 Ni plus 3 Cr3 pluses plus 6 electrons. So how many electrons am I exchanging?
6.
6.
The electrons, that N, is going to be the number of balanced electrons when I put the two cells together. Does that make sense to you?
Yeah.
Now, also, you have to look. You have to look at the overall reaction. My electrons are going to cancel out here, and my overall reaction is going to be trying to do this simply. Copy. Paste. Okay, so my overall reaction is this. Would you agree with that?
Sure.
All right, now let's figure out what my Q is. Remember, the equilibrium expression does not use solids, does not use water. So what is my Q going to be?
Ni cubed.
Is that, do we do reactants over products, Jolene, or do we do products over reactants?
Products
So
over
I'm
react.
going to take my CR. My CR3 plus concentration, and I am going to raise that to the second power. I'm going to divide that by my Ni2 plus quantity raised to the 3. Okay? So somewhere in my problem, I am going to be given.
Why are we only concerned with those two?
What else do you want to be concerned about, Jolene?
I don't know.
The only thing left in my equation is my chromium metal, which is a solid, or my nickel metal, which is a solid. And remember, solids do not appear in equilibrium expressions. Remember that?
Yeah, I do. I just didn't realize what was solid.
I was making an assumption. I didn't put in the little aqueous or solids.
Okay.
Are you seeing where I came up with Q now?
Yes.
So what I had to do was I had to get the original reactions, figure out which one was going to be reduced and which one was going to be oxidized. That set up my overall equation. The overall equation gives me my number of balanced electrons. The overall equation also gives me my equilibrium expression, which is my Q.
So what number would I plug in for CR cubed?
That would have to be given in the equation. The problem would be something like, we're going to do here, new slide. Okay. That would be your problem, Jolene. Okay. You know from the Nernst equation, I'm sorry, one more bit of information, and that is going to be at 25C. You know your overall Nernst equation is going to be why is that doing that? Your overall Nernst equation is going to be E cell is equal to E0 cell minus 0.0592 divided by n times the log of Q.
Yeah.
All right. We know that the standard potential was 0.48.
Mm-hmm.
E0 is 0.48. So I know that my E cell is equal. Is equal to a positive 0.48 minus 0.0592 divided by my N, 6 electrons, times the log of Q. Now, in this problem, my log of Q is going to be the CR plus 3 concentration squared divided by the Ni2 plus quantity cubed. So this is going to be my 2.5 quantity squared divided by 0.5 quantity cubed. Okay.
One over 12.5. The log of 1 over 12.5.
No, it's going to be 2.5 squared.
Yeah, but you could take it to the bottom and minus, and then you could say 2.5 times 5 is 12.5. Oh, that would be 1.25. So log of 1 over 1.25 equals, yeah.
Thank you.
And then 0.48. What is 0.0592 divided by 6?
0.0, for all intents and purposes, 0.1.
0.1 times the log of 1 over
6.25.
6.25. Five. We're doing log, right? Okay. 2.25. You have a calculator?
1.7.
Or what I say, 1.25? I was close.
Okay. And that's how you solve this particular problem.
Yeah.
Questions about this, Jolene, Nicole?
No.
Nicole?
No, sir.
Okay. Now I'm going to stop share and get back to the other screen, which is this one. In this particular experiment, There is no simulation, thank God. He couldn't find the simulation. So what he did was he has a video showing you. He also tells you you're not going to do the wet experiment. That's how it's done. What you're going to have to do is you're going to have to go down to the survey. And this may be different.
Yeah.
It may be different for every person. So just
Yeah.
be aware of that. But you have to, I guess because I'm an instructor, I can only preview. And what he does is he gives you, SC stands for the voltage of the standard cell. S means standard cell. N means non-standard cell. So what you're given.
Good morning, Sushi. Good. How are you?
You're not going to introduce me?
Come here. See? Here's one of my girls. Say good morning. This is my professor.
Good morning.
How you doing?
I'm doing fine. Jolene,
Good.
Jolene, you're too young to have a daughter that old.
Oh, I have older.
What can I say?
I
When you
have a lot of babies.
when
My
you
husband
get-
last night was like, do you want to have one more? I'm like, you're 50. No. You're going to be 70 when the kid graduates high school. No, we can't have any more kids. No way, Jose.
Yeah, what can I say? I'm 64, so what would that leave me? 80 something? No.
That's what I'm saying. Can you imagine being 70 years old? If your kid got married at 20, imagine being 70, walking your daughter down the aisle. We only have one boy.
In a walker?
Having more girls is
In a walker?
in a walker. If you still have legs. Oh my God. Can't hear. He's already deaf. Can't hear. Can you imagine? Do you give this bread away? Huh? Oh, that'd be so funny.
It's always nice to have that pin to burst the balloon, isn't it?
Yeah.
So
But I love him.
you're going to have to get to the survey to, you have to get to the survey to get this information that you're going to need to do the, report. And the report is really not that bad. So you're going to have one horrendous one and you're going to have one not so bad.
I think the horrendous one isn't that bad either now that I've watched it twice. I think I'm going to fly through it.
I'm happy for you.
I don't think it's going to be that bad.
Okay, so this report sheet. What time is it? Okay. Okay, so you're going to have this. This is going to be given to you in the survey. SC voltage and NC voltage, right?
Yep.
Okay. You're going to have the anode. You're going to have to tell me what the anode is and what the cathode is. All right. That's the only information that's new in this first thing. There's another page in that survey. It's going to tell you what the calculated voltage is and what the measured voltage is.
Then find the difference, and then the percent difference is obvious.
Bingo. So as I said, this is not that bad. There are some post-lab questions, I believe. Yeah.
These are the ones I hate.
This is simple. All you're doing is looking at zinc in that table, and you're looking at iron, and you're flipping one of them and adding them, just like I showed you.
That's it.
That's all you're doing here. The second one. Okay. Zinc and nickel. You're going to have to figure out between zinc and nickel. They had zinc and iron. Between zinc and nickel, you're going to have to figure out which one's going to be oxidized, which one's going to be reduced. You're going to have to get the overall reaction. You're going to have to determine how many electrons are exchanged. And it's going to be easy, +2 zinc, +2 nickel. So you got 2 electrons. So you're going to have the standard cell number. You're going to have the number of electrons. You just are going to have to figure out what Q is.
Is Q going to be, I'm going to guess, the nickel over the zinc?
Yes.
Good guess.
Wait. 0.76.
The nickel, right?
I'm going to flip it. Says... No, it's not.
Well, I don't have it. I don't have a chart.
Zinc is -0.76, and nickel, I believe, is a -0.26. So you're going to have to flip the zinc.
Okay.
So the zinc is going to zinc +2. So you're going to have the zinc 0.1 concentration over the nickel 1 molar.
Nicole, you like how I got a free answer?
I do. It was very smart.
I worked it, girl. It's called playing Southern stupid. No, I'm kidding. I really thought I was right. Damn. Okay, which of any measured
I'm sorry,
voltages
my mouth
differ?
is closed. If I say anything at this point, I'll only get myself in trouble.
Which, if any, of the measured voltages differ by more than 20% of the calculated value? So measured by, okay, and that will come directly from our chart from above. If it has a percent difference more than 20%.
Give me an answer. It's basically,
yeah, I mean, but if we have something that's more than 20% difference, that's really bad data.
But there could be something that's happening on the side
that we don't, like entropy
that
or
you
something.
Don't know about.
Off the heat.
I have no idea where he's going with this. Just give me an answer, okay? Don't leave it blank.
Butterflies and roses. Done. Okay, so the percent difference, we're going to do the calculated voltage or the measured voltage.
You're going to do the
denominator.
It's always theoretical minus experimental over theoretical.
Perfect.
Okay. So this is not that bad.
Trinity está bañero, Alan Clark.
Okay, any more questions? Because I've got to get back. I've got to get to my lecture.
Nope, this is great. We got to get to work. When is all this due? Because
Sunday.
Okay, perfect. So we have time to prepare for the storm.
Okay,
all
Sunday.
Right.
The other thing, Jolene, I am on Thursday. I am having a final review.
I'll be there. I'm going to look through the review and see what I need.
Questions, because that's basically what I'm going to judge, what I'm going to do on this.
Okay.
I have gone through, and there were 10 duplicated questions in the final. I removed them. So you're going to have 40 questions and 3 hours to do it in.
Okay.
Okay.
Some of the answers are going to be quick answers. Some of them you're going to have to actually do the math for.
How hard do you think it's going to be? Like, what'd you say?
For both of you, capable. All right. As long as you don't blow the final, you'll be okay.
Okay.
All right.
No, but I have to have an A.
Did you just hear what I just said, Jolene?
I know.
As long as you don't blow the final, you'll be okay.
But I have test anxiety. You know that. I call you every weekend.
Okay. I'm going to get out of here. Do you mind my showing your grades, Jolene?
Yeah, I don't care. It's no secret. It's a 93.2.
Okay. So it's a 93.2. I think I went through and told both of you that you have one bad one, that you probably should do both of these reports.
Yeah.
Yeah, I have one really bad one.
So the final's worth 250 points, 200 points. Okay, so let's say, and
the third one.
I need to get back into here. All right, syllabus. I just need to see how many points the final thing is. Okay, you've got a total of 1,500 points. All right. So of the 1,300, what is your average now, Nicole? Nicole, you know what your average is?
Maybe like a 95, I think. That seems high. Well,
okay, what do you want me to go for? 93?
it says I have a 95.
I'm sorry?
I think I have a 95.
Okay, I'm going to do Jolene's 93 because it'll save me time. Okay, if you somehow average your final average before going into the finals of 93, that will give you that will give you 1,209 points. All right. You need 1,350 to get a 90% or better. So you go 1,350 minus the 1,209. This means you have to get 141 points out of the 200 on the final to get an A.
Okay.
But this, I'm sorry, as I said, as long as you don't blow the final, you'll be fine. You can, both of you can be fairly sure, absolutely, you are going to get a B in the class. At least a B in the class. I know you don't want to be, but I'm telling you, Jolene.
Here's a joke. You want to hear a joke? The student goes to the professor and she says, I have a really bad grade. I'll do anything for an A. The professor's in his office and he kind of feels uncomfortable, but he takes advantage of the situation. He sits back in his chair and he goes, anything? She goes, oh yeah, I'll do anything. And he looks at her and smirks and he goes, are you sure about that? She goes, mm-hmm. He goes, how about study? It's good, right?
You got me.
Gotcha.
I'm sitting here thinking, oh dear God, this is being recorded. Somehow somebody's going to fire me over this somewhere down the line.
I'm politically correct. I just had to throw it out there. I thought it was funny.
So bottom line, guys, you get a 70 on the final, you're going to get an A. Okay?
Sounds like a plan.
All right. I will see you both on Thursday then.
All right. See you then. Thank you.
Take care.
Thank you.
Bye.
You're welcome.
Bye.